Chapter 17. All right. We have these things that we know are conductors, and we have things that are insulators, and we have semiconductors in between. And we know that conductors, what's the key property of conductors that we like? Well, hopefully we like it. If you're in a lightning storm, you might not like it. But electrons move very freely through conductors. Not so much with insulators. Doesn't mean you can't, but it's going to take a big force to force it through, a huge electric field to make that flow through. All right. In a conductor, our electrons move freely, and an insulator, they don't. They like to stay where they are. They're sort of stuck in the matrix of your chemical bond. Let me just tell you what current is right up front. When we talk about current, and with electronics at least, we have a wire, right? And we hook a wire up to a battery, and we hook the battery up to, we have a battery, a couple of wires, and a light bulb, and we can make a little circuit, which circuit means loop, right? A loop with a light bulb in there. And current will flow through the wire and light up the light bulb magically. All right? Everybody understands that? Everybody's done that before, true? Okay. So the question is, what does current mean? The battery, and this is we're going to talk about, we have really a good gravitational, is a good analogy between gravity, this situation, in that what a battery does, first of all, or a power supply, it creates a voltage, and a voltage is basically an electric field that it sets up, and it's basically how strong the electric field is. All right, so your voltage is a measure of electric potential energy. We have gravitational potential energy, how strong our gravity field, and if the higher I move something up in the gravity field, the more energy I store. Batteries are the same type of thing. It's amount of stored energy, a height you establish essentially in your electric field, instead of masses to drop for your charges to drop through. And the charges we typically are thinking of as moving are the electrons. So you can think of this hill, this voltage hill that you're on, and what we have is we have some electrons that will fall off the hill and accelerate and reach the ground. And so these electrons are going to fall off this hill like a river flowing off of a hill, and they'll fall down the hill and they'll fall to the ground. The taller the hill, the longer you have to accelerate, the faster and faster they go. The stream of charges, well, in a river we call that what? A current. What's a strong current mean versus a weak current? It's how fast they move. So a strong current means a fast current for water. Electricity is the same exact way. And so here's how it's defined. Let's say I were to put these into a pipe, all right, and that pipe is our wire, all right, and this could be like, gravity is the same thing, right? I actually could literally have a tank of water up here, right? This is a water tower for your town. I could put it up there, and this water has all this potential energy up here, and it's going to want to push its way through the pipe. The higher this up is up the air, the faster you will push it down. You have more water pressure because you have all this gravitational potential that'll push it through, and I can move this water faster and faster here the higher it goes. Electricity is exactly the same thing. And what gives me my hill is what's called my voltage in my battery. That gives me the size of the hill. 9 volts is a hill that's 9 times larger than a 1 volt hill. All right, it's a hill. All right, it's height. And the things that we're going to drop off that hill is not buckets of water or rocks or balls like we used to use in glass. It's going to be electrons. Or we could, I suppose, do the opposite and go down to the bottom and let positive charges out of our hand. And instead of flying down, they'd just fly upward instead, right? I like to think about negative charges, though, all right? So our battery basically establishes a voltage, which is an electric field, all right? And the higher that hill, the taller that electric field, the stronger the electric field. And this goes back to our idea of field lines. If they're very highly packed together, the electric field is larger, which would lead to a larger voltage, all right? And a voltage is, they call this a potential, voltage potential, because it sets up potential energy from this E field. Just like gravity, you have potential energy relationship, you have the same thing with an electric field. Any field force, this goes back to when we talked about conservative forces, every field force is a conservative force, and it has a potential energy function. The potential energy function for gravity is PEG, mgh. The potential energy function for an electric field is what we call voltage. So the taller this hill, so this is a 9-volt hill here, let's say, we have a 9-volt battery, versus a 1-volt hill. Our water flowing through this pipe, which are electrons, they have a longer time to accelerate. They'll move faster, and of course, the speed of this equals the current. And the definition of current is basically, if we have a pipe, and if we were to take that pipe and slice it through, and if we were to measure how many charges pass by in 1 second, that's what the definition of current is. The units for current are amperes, which we use in A for amperes, amps. All right, units for voltage are volts, V. So voltage this is called electrical potential energy. Electrical potential is voltage. Current they call ampere. I've named this guy's Ampere, an Italian guy, all right? And guess what the units are for current? It's coulombs per second. It's how many coulombs pass per 1 second, coulombs per second. And this is where 1 coulomb per second, so here's what 1 coulomb means. 1 coulomb per second is 1 amp. Is an amp a lot of current? Well, let me give you an idea of what an amp would do. I have these little motors that we run here. If I were to run these with, 9 or 12 volts, they'd be pulling about half an amp to an amp, all right? If I were to stall these and so that they had a hard time moving, the current jumps way up that it's going to draw to try to overcome the torque restraint that I'm putting on it. And so, but if I were doing these with those that are not very heavily loaded, they might be 400 or 500 milliamps. Milliamps means 0.4 to 0.5 amps. If I were to hold it while I had this voltage applied to it, these things would probably pull about an amp, maybe a little more than an amp each. All right, so an amp's not, huge amount of current necessarily. A toaster, on the other hand, if I were to plug a toaster in a wall, well, we can actually figure out, later on we'll figure out how much current a toaster takes, but it's going to be a lot more. Current is how fast charges move in your conductor. All right, so if you were to do a slice a cross section through your conductor and you actually measure how many coulombs of current went by in 1 second, that's actually how many amps. So that's what current is. How do you get electrons to move from one spot to another?
You get the opposite conductors.
Electric field. Yeah. All right, we establish an electric field. If I had an electric field this way, my negative charge is going to move in this electric field. My negative charge is going to move in what direction here? Up. All right. So if you think about from a negative charge standpoint, the negative is going to move against your electric field. All right. And so our electric field in this case would be which way? We've got an electric field that's pointing up. Here's my E field, okay? Batteries providing that electric field potential difference that we talked about before, and we'll look at that again later. So basically, by putting an E field across a conductor, you will force your electrons to start accelerating through that E field. Now, is there anything that's going to impede their motion, or is this like free falling? As I've shown, it's sort of like free falling here. Do you get any air resistance? Let's say you're an electron, and you're in take your conductor. Give me a conductor. What kind of conductor do you want to be in? What's the best conductor there is? Water? You're kidding me, right? Water's not a very good conductor. Don't be fooled here. Metal, please. Copper is one of the better conductors. 2 bonus points. That's one of the best. That's why we make wire out of copper, right? Well, he's in my physics class still. He's doing physics. CP. So copper is a great conductor. All right. Aluminum is a pretty good conductor, not quite as good as copper. Gold is a great conductor. All right. Nickel is a conductor, but not as good. Chromium is a good conductor, but not as good. Nickel chromium, nichrome, is a lousy conductor, which is a good thing because we use it for certain things. All right. Even though it's metal, it conducts, but not as well as the other ones. All right. So now let's put you in the shoes. You're an electron. All right. You're in a copper wire, and all of a sudden you are exposed to an electric field that causes you to accelerate. Is that free fall or not? In the air, would it be free fall? We drop a ball. Is it free fall? At a slow speed it is, but if we're on top of a tall cliff, pretty soon it's not going to be. You have air resistance. You have stuff that's impeding your flow. You're hitting air molecules, really, and they're whacking against you, all right? That doesn't happen with you in a copper wire, does it? You've got an electron, which is moving from that end of the room to that. It's like just a big, you get this big copper. You're going piece of copper. Imagine this big tube right here. Is copper wire hollow or is it solid?
Solid.
It's solid, right? It's solid inside. So let's say we had a big cylinder of copper coming down this whole room, and it's like you're in the middle of it as an electron. Is there anything to impede your progress from this point to that point?
Yeah.
What?
Let's go.
Now, you stop cheating here. Who said drift speed? You have an electric field that's pointing that way, and you're as an electron, you're going to want to go this way. So here I am. I'm going to run through it. I'm accelerating, but there's nothing to stop me, nothing to slow me down, right? There's no air to worry about. I'm at an atomic level. There's no air.
No, there's something.
What am I going to ram against? How about all your entire atomic structure? I'll be whacking into things. I'll be coming across nuclei, other electrons, stuff like that. So I'm going to be whacking at things as long as I go. So I don't have an unobstructed path, all right? So there is a certain amount of resistance I'm going to as I try to go through this medium, all right? Each material has its own degree of resistance to motion of electrons or motion of protons. You can actually have positive charge carrier that you can measure these drift speeds of for both electrons and protons. And electrons are much faster, by the way. But you have electrons moving one way. Now, it doesn't mean you don't have some electrons that are moving the other way. There is a little bit of random walk theory going on. Some electrons will be going the other way, and you'll be colliding with them, slowing you down. Some will be coming behind you, whacking you, but overall, you'll be moving from one spot to the next. And by the way, if I'm a wire coming from, if you're an electron starting at the power company, how long does it take you to get from the power company over to Tingsboro? Well, in reality, you never get here because you're really you'll move a little bit of a distance, and you'll be captured by another atomic bond, and another one will take your place and move on. So really, we don't move electrons the whole way. All right. How fast do those electrons move? How fast does that power move through the wire, do you think? So if you turn on the power at the power plant, how long does it take for the light bulb in your house to light? Instantaneously? Well, if you look at the speed of the charge carriers themselves, they don't really move that fast. All right. So it'll take quite a while. It might take, I don't know, if you're 100 miles, they give you some drift speeds of different things under different conditions, and you can calculate. They don't move that fast. What moves fast, though, is your electric field, because that's moving at the speed of light, essentially. You set up an electromagnetic wave that's actually going through here. It's really your electromagnetic wave that's moving through your wires at it's the speed of light, and so you still get that instantaneous effect. So all your electrons in that path, you get this electromagnetic wave that blows through, and that electromagnetic wave is then going to move your conductors. And so there's a speed of light acting on these things, essentially. But as you're moving along, though, you're colliding with things on an atomic scale, if you want to think about that. And every collision you have what's going to happen when you collide? What happens when we collide? When things collide, what happens? Well, you have all sorts of momentum, things like that, but what happens? Energy is never lost, per se. But we're going to change energy to non-conservative probably. We're going to get some heat, right? So that resistance is, you actually have these collisions, these particle collisions. You want to think about it in that simple model form where you get these collisions. Now, the nice thing about these collisions, you could say maybe they're perfect collisions because remember I was saying if you get two magnets, they won't actually touch each other. You could say maybe it's the same thing here. You get two electrons when they collide. Do they really collide or do they sort of do these bounce off because they can't really touch each other because they don't physically actually touch? But you actually get heat generated, all right? That's what's happening in a light bulb, right? As you pass electrons through there, they're trying to fly through there, but they're in a very highly resistive material, but they're being pushed really fast, and then you have these massive collisions, so it heats everything up, and when it heats things up, they get hot, red hot, better yet, white hot, all right? And you cause these excitations of your atoms, and so you push electrons into these high energy states, and then drop back down and emit photons, and that's where your light comes out of. All right, you're exciting atoms through these collisions, through these high resistive things in your filament for an old filament light bulb. All right, and so each material, whether it's copper, whether it's gold, whether it's silicon, whether it's glass, you name the material, it has a specific amount of resistance per unit length or whatever you want to call it for that material, and you can look it up on a chart for each material. All right. And so let's talk a little question about here. So here's a wire. All right, here's my copper wire. All right. Let's say I have a whole bunch of electrons that are going to come through here. Where are those electrons going to be? They're going to be all through here, right? I'm going to look at the cross section here, right? They're going to be coming through like this, right? Flowing, I don't know, this way or that way. So they're going to be distributed evenly throughout here, on the outside edges, on the inside, everywhere else, right? On the outside. Our conductors, our electrons, if I have an excess of electrons that are moving along this, where are they going to be? And there's not going to be any inside. They're going to push all the way outside. And so this goes back to our I talk about when we're doing chapter 15 topics. Our excess conductors on these things are all going to be running the outside of the wire. So really, what's on the inside of the wire doesn't really bother the electrons too much. So I could actually have a hollow copper wire to save my money on some copper, and because all the charges are all moving on the outside of it in any case, as it turns out. All right. What?
Why are they solid then?
Have you ever tried to make a hollow wire before? It's a manufacturer. However, has anybody heard of a hollow wire before? This is 2 bonus points here. Has anybody seen a hollow wire before? What? You got to give me what it is. What kind of hollow wire?
It was...
Where have you seen a hollow wire?
Okay, that was a lie.
It's a lie.
Yeah.
How about coax cable that your video comes in on? If you cut a coax cable, you have an outer sheath and you have an inner conductor.
But that's a cable.
Yeah. A wire and a cable. It's the same thing. So yeah, you can do it. You can build a hollow cable, and you have a conductor in the middle.
Like a bunch of wires.
And you're actually, it's a waveguide because in between you're actually containing a wave inside there, so that you're not actually moving conductors as much as you are waves in a waveguide.
But isn't a cable technically just a bunch of wires formed together?
No, it depends on the wire. I mean, let me show you what I mean here. So wires are. It depends on the wire. I mean, I have some big gauge wire at home that's solid through and through. This is made up of many strands twisted together. Still, even though it's many strands twisted together, are the electrons going to be the outside of each individual strand? Or because these strands are touching together, they're still going to be the outside of the entire thing. So why do we have all these different strands? What's the purpose of that? No, I mean, the diameter is the diameter of the diameter. They're all going to go to the outside. Yeah, but I can just make a big fat wire. Why not just have one big fat wire instead of all these tiny little ones?
Do they still go to different purposes?
No, it's still, volume is volume. I could just as easily put solid core wire in here, and it would carry the same amount of electricity.
What do those go to different places?
This is easier to bend than that way. But the more importantly, this is a mechanical engineering issue with wires. Number one, you can bend it a lot easier, so that's 2 bonus points, I would say. And for small gauge wire, I'm like right now in our electrical engineering class, or our don't tell my kids I said it was electrical engineering class. In my engineering class, they this in here, in this wire here for this little car, this is actually stranded wire. So I don't know, maybe there's like 10 strands in each one of these things, all right, which makes it flexible. But solid core wire at this gauge is easily flexible too. The difference is, this is an interesting thing, they don't ask you on the exam about this, but if I were to bend solid core wire back and forth 7 times, it'll snap. That's my rule of thumb. I tell kids, stop bending the wires. So they'll sit there all day long and bending wires and breaking all my wires. Solid core wire, I can break this type of gauge wire. You go 7 times and it'll be broken. Just like a coat hanger. You ever bend a coat hanger back and forth and it'll eventually break? And by the way, if you touch it while you're doing it, it gets really, really, really hot.
Wire or coat hanger?
A coat hanger wire. Just a regular coat, any type of solid wire. I don't care what material it's made of. But if it's stranded, it turns out you could go back and forth 1,000 times probably and it won't break. And so it's a nice property, material property where, and this deals with the mechanical engineering properties more so than electrical properties. So that's a little side note here. All right. So all right now. What would help us then on this wire? First, so we have something. Every material has its own has a resistivity. We call it. Every material has a resistivity associated with it. Resistivity. And the letter we use that for is rho. Okay, another Greek letter. All right. Copper has a rho. Gold has a rho. Glass has a rho. And the higher the rho, the more conductive you are. All right. And which is which? I got to remember here. Is rho conductivity or resistivity? Because you have these are just reciprocals to each other. This one's for resistivity, and 1 over rho would be your conductivity. All right, and that's just a number. You can look up that number, and they've measured it and they look it up. All right, so you could make, if you were to manufacture a wire, the question is, what would you want to do to make that wire? Let's say you want to manufacture some wire, and you want to make it. All right, what would you do to make it as conductive as possible? Yeah, you want rho to be low. All right, so the first thing to do is we want rho to be low. What else would you do? Think of our geometry of the wire. What kind of geometry would we want? If you want to make it through this wire as fast as possible, what do you think would help you in terms of the geometry of the wire? The wire doesn't really, they can go through turns. No problem. Turns aren't a problem for wires, for conductors. They don't really care about doing turns. What do you want? A bigger diameter or smaller diameter? Larger diameter, why? There's more room for all the charges being there, so if I have 1,000 charges, they have more space to spread out. They're not bothering each other as much, and so they can flow through. All right? So we want the diameter, we'd want to increase. All right? What else? All right, remember, put your stuff in this pipe. You're running through this as fast as possible. What would you prefer then? What? Well, copper's copper. You got what you got, all right? Or whatever we're using here, copper, whatever, all right? What's the other thing? Well, yeah, that's our rho, though. Rho is our material. You pick a rho, that is a material. Each material has its own rho. All right? Copper and gold are really close to each other. I mean, you can make gold wires, you make copper wires, and they're going to have roughly the same properties. So that's why we use copper, not gold. The only upside of gold, which they use in electronics, is it doesn't corrode. All right, so it doesn't oxidize. Copper oxidizes, gold does not. Gold, I can bury my ring in the ground and 1,000 years later pull it out. It's going to look as shiny as the day it was put in there. Copper would not. It actually corrode right away eventually.
Right away eventually.
Yes, right away eventually.
Could you control the amount of...
I didn't mean right away in that sense. Corrode to nothing eventually. So I can increase the diameter, which is really the cross-sectional area. All right. What else could I do?
What if you put less electrons per second?
Well, you want to move through that as fast as possible. We're trying to make wire because the less resistance they have, the faster we can go through it. We want to get from one end to the other as fast as possible. So what's the other thing you can change about the geometry to get to the other end as fast as possible?
Shorter length.
Rockets. Do what?
Shorter length.
Make it shorter. All right. Make length go down. All right. So I think you got 2 bonus points for each of you guys for the diameter and the length. All right. So it turns out the resistance of a wire. All right. Here's the formula for the resistance of a wire. All right. You can take the material property, copper, whatever, has its rho. All right. So if you want a really low resistance wire, pick out a material that has a really low value of rho, like copper does, gold does. If you want a higher rho, well, make it out of glass. Good luck conducting through that. If you double the length, what's going to happen to your resistance? If I double the length, my resistance doubles. If I double my area, my resistance halves. if it's a circular cross section, if I double my radius, your resistance drops by a quarter, because R squared, right? So here's another 1 over R squared relationship for you. A little bit different radius here we're talking about. So typically our conductors are I don't know, not always, but typically when we're talking about conductors, we're talking about wire, and typically wires are formed in circular things. So we're really talking about area of a circle here, pi R squared typically. All right. So you can actually calculate I can give you, like this wire right here, we would effectively use not the diameter or the radius of one of our individual strands. We use the diameter of this entire strand. We can look up copper, all right, and then we could say, all right, what length do we have here? And this is a big cable that came out of MIT Haystack's observatory for running one of their big, all their motors to move their antennas around, their radio antennas. And so they need a huge amount of current. And if you have a huge amount of current, you got to put that means you got to move things really fast. Huge current means fast moving electrons. That's all current means, right? Current is the speed of the electrons passing through something. So if I want to pass a really huge current through something, I'm going to need something that's resistance, just so it says before, resistance is the property which resists the motion of electrons. Because electrons are the charge carriers that move more so than their positive charges. But positive charges do have if you look at the subatomic level or the atomic level, you will see, you can visualize our little jumping of spaces. You can see sort of like positive charges move in a sense. And there are drift currents for positive as well as negative charges. So resistance is a property which slows electrons, is the way we want to think about this, or charges. All right. So if we want to have low resistance, allow them to travel as quickly as possible, because we need a lot of current to do a lot of work. Your current's going to do some work for you, essentially, right? You're putting all this kinetic energy into these things, and they're going to do something. All right. They're going to do some work for you. So if we want to do a lot of work, we need a lot of speed here. That means we need a lot of current. If we need a lot of current, we need low resistance. And if we want a low resistance, what are we going to do? We're going to pick a low resistivity. We're going to increase. We shorten our length as possible. So we make our cable runs as short as possible. We wouldn't use twice as much. We wouldn't put things in a S pattern going to the thing. We go point to point. All right. So we keep our length short as possible, and we keep our diameter as big as possible. This is some pretty hefty wire here. So we could actually calculate on this, we could actually calculate the resistance by working this through. And then when we use Ohm's law and a couple of other laws coming up, we can actually calculate how much current can flow through this without overheating it too much and things like that. All right. Have you guys ever used any devices where you had a really, really long extension cord and the extension cord gets hot?
Yeah.
It would have to be something that pulls a lot of current, like using some sort of big machine. All right. I've had things to extend as well. This gets to voltage. You actually, we'll talk about that. We're going to switch it next into current. Looking at circuits. So I think we just covered everything in Chapter 17. Resistivity, temperature variance, resistance, superconductors. Yeah, so we've covered most of this. There's a couple things. I'm going to show you how we can measure this. But basically, I've used some machines before where I had a really long extension cord, and it's just an outdoor power tool, and the thing ran slow because you actually not only do you impede the flow of current, flow of electricity through there, you're also using up part of your. Remember that voltage is potential energy? Well, part of that potential energy is being used to push all those electrons through that wire, and you're using up a good chunk of your electricity in your wire rather than in your device you want to use it in. So rather than blowing all of your thing by having all these collisions, by having all this high resistance, I could buy an extension cord, which is instead of like a 14 gauge wire, which is a measure of how thick the wire is, I could go down to a 12 gauge or a 10 gauge or maybe even 8 gauge wire, because you can go buy some industrial You won't find them at Home Depot. You can get like 12-gauge extension cords, but you can get some ones that are used for industrial purposes that maybe aren't quite this big. I mean, for certain big industrial purposes, you'll see extension cords like this, all right, which can do huge amounts of current. So that's a resistance. Now, if you were to do a little experiment here, and let's draw a circuit here, all right. So if I were to take a circuit, and I can draw it like this, all right, and a symbol for a resistor looks like this. That's a resistor, okay. And a circuit just means a loop, all right. And in this loop, I'm going to put a battery. Here's a symbol for a battery, all right. And this is a DC battery.
I have a question.
All right. All batteries are DC, by the way. All right. All right. And let's just say that we're 9 volts. Question?
So, like, at home, I have, like, a 6-foot phone charger and a 3-foot phone charger and, like, a 6-inch phone charger. Would it charge faster than the smaller one?
Well, here's the other thing about this. This is where this is leading to. I'm going to talk about wires in a second here. If you try to drive a huge amount of current through it, yeah, your wire you'll actually physically feel your wire heating up. If you feel your wire heating up, that means you're overloading that wire, and you're losing a lot of your energy and you have power loss in that wire, where you want it to go to your device at the end. But for typical conductors, we treat conductors as zero resistance, which means we have zero voltage drop. For typical purposes that are designed for, the resistance of the wire compared to the devices that you're actually driving is negligible. All right, so there's our free fall analogy, right? We're free falling through the wires, and we stop free falling when we hit what we call our load, and that's where all the work is done. So when we're free falling, we assume wires are basically ideal conductors. An ideal conductor has no resistance. All right. So when we're doing this circuit analysis, that's the next thing we're going to talk about is circuits. We have to look at where the resistance is, because that's where all the work's going to be done, all the heat generated, and all the work. And heat is one thing we get out of electricity. What else do we get out of electricity? So heat is one output we can use to change it into electrical energy, into heat energy. What other forms of energy? Light. Is that directly done, though, or is that through heating? For an old-fashioned light bulb, you heat up a filament, and that's still heat. What? Yeah, new LED lights, you're doing a quantum transition, so you're pretty much directly making a quantum transition happen to create a photon. So for modern lighting, LED lighting, it's a quantum transition that happens. For this lighting, the electricity creates a really huge electric field, in other words, a huge voltage, like 10,000 volts, and excites your atoms, and then when they excite up whatever your fluorescent fluorine in here, it's really mercury is the main component in this that you're causing to fluoresce. Fluoresce just means when it hits the tube, it causes a reaction that causes an atom to be or an electron to be bumped up to a higher level, then it drops back down and it emits a photon. That's what we're talking about when they're fluorescing. But basically, the medium what you're doing that through is we take mercury gas in those, and we put a huge electric field across, a huge voltage, and any atoms in there, the electrons are going to get excited way out into their top energy levels, and then at some point in time they'll drop back down. When they drop back down, they're going to release that energy they had up here. That energy comes out as a photon. And for these, actually, the photon turns out to be a really high energy photon that would be harmful to you. But the inside of these tubes are covered with this powder that has a fluorescing powder on it, and it hits that with high energy, absorbs it, and then causes a secondary chain reaction of an excitation, then a drop again, and it gives us the light that we see here. So you got sort of like this chain effect up there. But that's not what let's talk about this. So a DC, batteries are what we call DC, direct current. So we're talking about voltage here, but we're talking about current. What's the opposite of direct current? So AC is alternate. That's right off right here.
Hold me back.
And here's, if I were to draw a graph let me just draw a graph of voltage versus time, or I could do current versus time if you want to talk about the current part of this. Because I could actually supply a current to push through a wire, or I could provide a voltage, which would then pull a current. So having a current source or voltage source are really two sides of the same coin. So here's an alternating current. All right, where we'd have so much, whatever value of current here. All right, let me draw this in different colors so you can see. Here's the level here. So what it means, it's just a constant level voltage that we're going to apply to this. That's what all batteries are DC. They give you a voltage level, 12-volt battery, 9-volt battery, 1.5-volt battery. Lithium-ion is like a 4.2-volt battery. And that's a chemistry issue you're talking about with that. And so for DC just means I have a constant voltage that I'm providing here, a constant size hill for those electrons to fall over to accelerate to a certain speed, which gives us that speed is our current. All right. The taller the hill, the faster they go, the more current we have. All right. Alternating current or voltage essentially means your voltage is actually oscillating from a positive to a negative, positive, negative. And if you were to measure this coming out of here, it's 60 hertz, 120 volts. 60 hertz means what? Every 1/60th of a second, I do one cycle. Remember, hertz is frequency terms, right? That's 60 cycles per second is hertz. So our voltage here cycles in these lights and everything else 60 times per second. It goes through a full high to low, back to zero again. All right. So this is for standard power. We're talking 1/60th of a second. All right. Well, that's not very fast. Your telephones are gigahertz. Okay. To give you an idea here, right? And our current would be doing something similar that you're driving. And what's our peak voltage on here? If it's 120 volts. 60 hertz, so what's our peak to peak here? Well, what's our amplitude? Nope. Nope. It's 157 volts. What's wrong with you?
Oh, my bad. Obviously.
It's 120 square to 2. Come on. It turns out this is a root mean square voltage. So
I won't get that wrong.
So it's like 120. It's 120 squared to 2 actually. But that's another story, all right? I got you on that one, didn't I?
We'll get to that at 6 o'clock.
Now, all right. Here's a typical experiment we do, all right? The question is, if we have our little simple circuit here, and I'm going to put this arrow here so we have a variable DC voltage supply. All right. So if we have variable DC voltage supply and we have our resistor here, first of all, I want to measure on this resistor. And by the way, if you want to see what a resistor looks like that we use in electronics, these are resistors. These are examples of resistors. All right. These are examples of resistors. All right. Now you notice this one is actually these ones are physically larger than these ones. And it's larger because, I have 167 different values of this size resistor, of this physical shape right here. But they all have these little color-coded lines on them, and you can read those. These are color codes, and you can actually read what value it is. And there's a little chart here I have, and they actually use Roy G. Biv, the colors of the rainbow, to actually count out the numbers. The size of the package doesn't tell you how much resistance this has, all right? And so inside, I've got a metal end and a metal end. How much resistance is in metal? In an ideal conductor, the resistance is 0, all right? So we essentially say, if I were to measure the resistance, I literally could not measure it on my voltmeter. All right, let me get a voltmeter. I want to show you how these things are measured. So I can actually measure the resistance of this guy. And if I look at these stripes on here, I've got orange, white, brown with a gold. All right, and the first three ones are the ones that matter. So orange is what?
2.
Orange is what? Orange is what?
1,000.
No, there's a number. Read it off this thing.
2.
Read that column only. Orange.
3.
Orange is a 3.
Yeah.
What else? White's what? 9. So this is a 39, and now the next number he's going to give you is the number 0. Brown.
Yeah. 1.
So that's 10. So I got 39 with 10 is 390, and the gold means it's how accurate this is. It's plus or minus 5%. So it could be anywhere between plus or minus 5% of that. So if I measure this, what do I got? 385 ohms. All right. Ignore that decimal point there. 385 ohms.
390.
So it's supposed to be 390, but I have plus or minus 5% tolerance on this. So 5% of 400 is 20. I can do plus or minus 20 ohms off that, and I'm only within 5. So I'm well within the 5%. I'm actually 1.25% off, low. All right. So there's a little tolerance you can have on that.
Easier to read. This one doesn't even have
now, the typical experiment you do is this. I'd say, all right, what if I vary voltage from 0 to 1 to 2 to 3 to 4, blah, 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 volts, right? And if I measured I, so this is our independent variable. And the reason I'm picking voltage is because typically our power supplies, we actually control voltage in our power supplies. There's a knob that says V on it, not a knob that says I on it. All right? So we're going to measure I. All right? The question is, if we were to measure these values, and this would be a lab experiment that we do, and if you were to plot this, what would you get? If you were to plot V here and I here, what shape would you get is the question. All right? It turns out your data would look like this. Well, your data would look like this, in a perfectly straight line. So if you were to do this experiment, this lab experiment, so we had some resistor, some unknown resistor, and if we were to vary, so we varied voltage. Now you notice, this is my independent variable, but I plotted it on my y-axis. That's okay, I can plot it wherever I want to. But the reason is because the formula we use, turns out I solve for V all the time, all right? So this is actually my independent variable. I did put it on what typically uses as a dependent variable. All right. So it turns out this is a linear relationship for these type of resistors. And if you were to draw a line through this, if I were to take that resistor and do it, guess what the slope would be? My slope would be 385. So it turns out my equation for this line would equal V equals 385 times R, times my current, I. All right. Turns out this is my resistance, so I get V equals IR. All right. This is called Ohm's law. Very critical equation. So do our circuit analysis. So now we're in chapter 18 now, circuit analysis. All right. So this is Ohm's law. And this is for, this relationship holds to, this is called an ohmic device. Any type of, or material. Now, by the way, the material inside of these, we've got a metal wire, and this little thing in between. Guess what this little thing in between is made of? It's some material that conducts, but not perfectly. Silicon. He's saying this because it's a semiconductor. It conducts partly. All right? Not silicon. Turns out it's carbon. Carbon actually conducts to some extent. And if you mix different impurities into it at certain ratios, you can vary the amount it conducts, and you can very carefully in a manufacturing environment control exactly what the values are here. Like I said, over my drawers over there, I have these exact same shaped devices that go from, I don't know, a couple ohms up to a couple million ohms in the same shape of device. And all they're doing is varying the impurities in this composite of materials, which carbon is one of the key components in it, to make it more or less resistance. And they can control it very, 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 very accurately. All right? So I have some good stories about that. So I went to a manufacturing place, I saw this happen before.
They have them labeled.
Lower right, look in the green drawers. Pick out something from the top drawer, and then pick out something from the bottom drawer, because those are my lowest and highest, respectively. So if you're to do this little lab experiment, you could actually figure this out. Now, one thing I want to show you is how do I actually measure something in a circuit, all right? So this is my power supply here. This is my resistor here, all right? By the way, you could put a switch in here, too, if you want to turn a circuit on or off. A switch looks like this in a circuit. This is the symbol for a switch. All right. So by pushing that switch down, I actually complete my circuit and current flows.
These are right ones, right?
Yeah, so here's a 2.7 ohm resistor, and here's an 820,000 ohm resistor. And he went low here. I mean, I have 10 million ohm resistors, too. And they look the same, except for the color stripes on, but the same size, all right? So why do I have some that are a bigger package? This one's a bigger package. Why do I want a bigger package? Because I have this same resistance value in the same size package. These are tinier ones. And I have some that are, huge packages. Let me just show you. This is ceramic. Sometimes it's ceramic. How many ohms do you think this is? How much resistance? Big or small?
I'd say probably pretty big. No.
Average amount is a trick question.
Oh, resistance.
Resistance. This is the ceramic material here.
Small.
10 ohms. 12 ohms. Small.
Wow.
It's small. This ceramic, so why, I mean, I have 12 ohm resistors that look like this, too. So why do I want a big package like this? Why did I want a bigger package for this one? It's a radiator. The bigger the radiator, the bigger the size of the radiator, the more effective I can distribute heat off of it for high power applications, all right? So the size of this physical package is basically the size of the radiator to allow it to radiate heat so I can push more current. I might need a 12 ohm resistance to get a lot of current through something, but I need to be able to get rid of the extra heat that results. So this is the big radiator on it. These are 20 ohm resistors, and they're in this anodized aluminum package that looks like literally like a radiator fins on it. And they're in this big aluminum package with radiator fins so I can take heat and suck heat off of it. Those are 35 watt power transistors. I can radiate 35 watts of energy off of that, which is a huge amount of energy. These are rated for 10 watts. All right, so I can radiate, which is still a lot. These get hot, but they're designed to be hot. That's designed to be even hotter. This package here, I can only, this is a quarter watt package. All right, so I can only have a quarter watt of energy off of that. If I do more than that, it burns. It'll actually start smoking and turn black. This one does a half a watt. All right, you can get small ones that are like 8 watts or whatever. And I have some ones that are like 2 watts that are just bigger and bigger sizes of these, and then they get into this size. All right. So so these are ohmic. All these resistors I'm showing you are ohmic. All right. When you heat something up, because that's what's going to happen. When we push current through here through a resistor, you get heat. Heat is your byproduct. All right. Which may be what you want. For a toaster, that's what you want. You want the heat. All right. For electronics, generally speaking, you don't want the heat. All right, so that's why you have the radiators to suck off the heat, and you have blowers to blow it out on your computers. That's what your blowers are for, to draw air through, and you have all these radiators inside. You got to pull air across them to get the heat out. When you actually heat something up, it actually changes the material properties a little bit. If you heat an object up, what do you think happens to the resistivity of the object? Goes up or goes down? Think of the atoms. What do the atoms do when you're heating something up? They're vibrating faster. Now you got to run through vibrating atoms instead of stationary atoms. What's going to happen? You're going to collide a lot more. Your resistance goes up. So resistance is, to an extent, heat dependent. All right. So, and for a non-ohmic material, if this is an ohmic material, what do you think a non-ohmic material would look like if you graphed it? A V versus I curve for a non-ohmic material. It'd be a curve. Wouldn't be linear. All right. Needs to be non-ohmic. It's non-linear. But any resistor you see like this, you could assume, if they don't tell you otherwise, that it's ohmic. Use Ohm's law, V equals IR. All right? So nonlinear is non-ohmic. So you can't use this little simple relationship. That's the key relationship, folks. Nonlinear, non-ohmic. By the way, Ohm is named after this guy named Mr. Ohm. He's George Ohm, German, Prussian guy. He was an instructor, high school, advanced tech school instructor, and he came up with these properties back in the 1800s. So this is an easy experiment to do. Now, let me show you how you hook up device. How do you measure voltage and current? Let me just do that on the next page here.